Good morning, everyone.
Good morning, sir.
Good morning, sir.
Uh, I hope my screen is visible.
Yes, sir.
Okay, so yesterday we had discussed about the losses and how power budgeting helps a designer in designing an optical communication point-to-point link. Fine. So going ahead, yeah. So um, this is a example, another example of how this optical point-to-point link power budgeting can be useful. So power margin, I think I had also mentioned about this in class uh, some time back. So yeah, this is what I was talking about. So we had a jumper and a connector. So jumpers, uh, okay, one end is probably the source end, and the other end is probably the receiver end. So that is the reason the jumper is not being considered with two connectors. Fine. So this is the same as what we had discussed yesterday. Okay. So accordingly, what is the power margin? Means how much power you are getting more than the desired limit, desired minimum power at the receiver. So you have 7 dB more at the receiver than the minimum sensitivity of minus 32 dBm. That means you would be getting minus 25 dBm at the receiver. I hope that is clear. Going ahead, there's the next part, which is the rise time budget. Uh, this expression that is given here is not properly displayed. Mm, well, what are the basic parameters which limit the system speed? These are the transmitter rise time, the group velocity dispersion of the fiber, modal dispersion, and the receiver rise time. So these are basic parameters. So if you are using a single mode fiber, then the modal dispersion rise time will be insignificant, but the group velocity dispersion would still be there. Fine. Uh, Let us go to, just give me a minute. Okay, uh, I believe this is visible, right? This
Yes,
is
sir.
this is from the book. Fine. So the total system rise time. This is given by the sum of four components here. TS here refers to the source. D refers to the detector. So rise time is usually calculated for the time taken by the pulse to go from 10% to 90% of its value, of its final value. So TC is the uh, well, Tn is given here. It is yeah, intermodal dispersion. So because of intermodal dispersion, you have the rise time Tn, and intramodal dispersion will again give you another rise time. So this intermodal and intramodal, intermode refers to uh, dispersion between two different modes, right? And so this is what is present in multimode fibers. Okay, so this factor is present in multimode fibers, whereas this chromatic or intramodal dispersion is because of the group velocity dispersion, and this is what is given by Tc. So in case of single mode fibers, this term will be absent. Fine. So this is the overall rise time for the entire system. And going further, mm, there is the output response of the photodetector and the circuit after the photodetector. So usually there is a RC circuit in the after the photodetector to filter out high frequency components and allow the necessary signals to pass through this. So when the input voltage is of this form, a step input, then what you can expect is a slowly increasing value of the output at the output of this RC circuit. Fine. So the rise time associated with such a circuit is 2.2 RC. And this is the frequency response or the transfer function of this particular circuit. So this would be a part of TD because this is coming from the detector. Okay, so if TD indicates just the rise time because of the detector, then it is not included. But if we say TD is for the whole receiver, then this 2.2 RC would be included in that. Fine. So depending on how TD is defined, this may be a part of TD or it may not be a part of that. So this is about the uh, rise time or the rise time budgeting. Have you read about these line codes?
Yes, sir.
डिजिटल कम्युनिकेशन में पढ़ा हुआ है? किस में पढ़े हो?
Digital communication.
Okay, so these are similar, or I shouldn't say similar, but the coding techniques are the same. Fine. So what is used in digital communication is also applicable here for encoding. So I have anyway, I have already shared this these slides in Google Classroom. So if you go to, yeah, so if you go to this classwork in slides, previously there was just chapter 2 and chapter 3. Now I have included this analog system and digital optical communication also. So you can go through these, but in these slides, wherever you find equations, you better cross check with what is available in the book that I have already shared here. Uh, in this book, you'll find the necessary correct equations. Fine, because some of the equations have not come properly in the slides, just as the one that you can see here. Okay, so in digital transmission, line coding plays an important part because errors are a natural phenomena which you cannot completely eliminate because of the random nature of the signal, the input signal, because you can have very fast fluctuations in input, and because of the imperfections in the fiber, uh, and even because of other nonlinear effects which can arise because of high optical powers being transmitted in the fiber, errors can always creep up. So in order to uh, correct some of those errors or to minimize the errors, line coding formats are introduced so that you have proper digital information which is being transmitted. So among these line coding techniques, there are not just these three, but there are many other formats which are used. So the non-return to zero, return to zero, and the phase encoded format are just three of the many uh, uh, formats. So these are two-level codes. Okay, so even multi-level codes can be used, but yes, in optical communication systems, multi-level codes are usually not preferred because that when you use multi-level codes, then elimination of additive noise becomes a bit difficult. So this is about NRZ codes, which refer to non-return to zero. Since you're already familiar with this, I would go into the details. So this is about NRZ codes, and yeah, there are certain problems associated with NRZ codes. If uh, you have a continuous stream of ones, then the signal level drops, as you can see at the end here. So what is defined as the baseline wander. So this can occur when you have a sequence of ones which are transmitted uh, together. So, mm, so scrambling is a method in which you can eliminate this baseline wander, or of course block codes can also be used. Mm, So return to zero codes eliminate these are another format which eliminate the uh, problem of baseline wander which is there in non-return to zero line codes. So another advantage that you get with unipolar, with return to zero codes is if you look at the pulse width, right? This and this, the pulse width of the return to zero format is half of what is for the NRZ format. So if the pulse width is lower, the power necessary to transmit this is also lower. So RZ is slightly more power efficient, but of course, RZ is more power efficient, but it again has its own problems in that when you're transmitting lower amount of power and the pulse duration is low, you need to be sure that the pulse which you're transmitting is able to propagate up to the receiver. And of course, even the pulse width, since the pulse width is smaller, uh, it's possible that the pulse may be missed at the receiver if the attenuation is um, high. There's another type of coding which is Manchester coding, which is another way of transmitting. So Manchester encoding does just a direct modulo 2 addition of the baseband NRZ signal and the clock signal, and this ensures that there is a transition at the center of each bit interval. So to decode this means to get the signal back, what the receiver needs to do is just check where all there is a transition. So if there is a negative going transition, or you can say a falling edge indicates a 1 bit was transmitted, and a rising edge would mean 0 bit was transmitted. So I believe what is given as the bandwidth, uh, this says the bandwidth is higher because the pulse widths which are being used are half of what you have for the NRZ. So when the pulse width is half, then the bandwidth also needs to be twice. So block codes are another class of codes which uh, not only which are not only helpful in uh, just maintaining or finding what is the level of the signal, meaning if you're receiving something, then the line codes can, I mean the NRZ, RZ, and Manchester codes, these can tell you whether you have received a 1 or a 0. But the Manchester coding or the RZ coding or an RZ coding, these will not be able to correct any errors. So this block codes have the added advantage of uh, error correction. Okay, so block codes by itself are a completely uh, it's a completely different subject altogether. But I can just give you a very simple example of error detection. Okay, so I think you all must have read about what are parity bits, right? And parity check. So you have an odd parity and an even parity. So if you're using even parity, then you count the number of bits. If the number of bits are odd, you insert one more parity bit, which would be 1, to make the total number of bits even. Uh, uh, and if the number of bits are already even, then the parity bit which is added would be 0. So, so at the receiver end, if the number of ones is odd, then the receiver can identify that the received block has some error. So this is what is known as error detection. So block codes are more advanced codes. These have much more advanced features. These are based on linear algebra, and the block codes can even correct errors at many locations. Okay, so the use of block codes is very popular in all communication systems, and uh, these come under the category of forward error correction. So any practical communication system includes forward error correction, and depending on what is the channel, it can be different types of forward error correction forward error correcting systems which can be employed. So block codes is only one type of um, codes which do error correction, but there are also convolutional codes and yeah, uh, it's basically divided into the coding theory is basically divided into two categories. One is the block codes, and the other one is the convolutional codes. So, but of course, going into those details is right now a bit too much of depth. If you're interested, maybe in the next year, you may be going through a course on error control codes. So that would be covered there. And uh, so this is a comparison of different codes. So what is represented here as MBNB, it means There are m number of bits at the input of the coding system, and at the output of the coding system the number of bits increases, just as you do for a parity checking. For parity checking you are adding one bit, so n is m plus 1. But in case of block codes this can be much higher. There are systems wherein you can have 4 bits at the input and 7 bits at the output, and it's even possible that you have 5 bits at the input and you get 15 bits at the output. Okay, so there are different types of codes, and the different types of codes give different error correcting capabilities. So this is a comparison of different types of codes. So this ratio n by m indicates how much bandwidth increases because of this coding, because of the introduction of this coding. Uh, and yeah, I mentioned about forward error correction just few minutes back, and we are here now. So forward error correction means you introduce some redundant bits, and that inclusion of redundant bits would enable the receiver to identify where the errors are. So that is forward error correction. And automatic repeat request, this is based on error detection. So the receiver does not have the full capability of error correction, but it has a capability of error detection, like say some parity checking method or something. So in such a scenario, if the receiver detects that there is an error, then automatically it will ask the transmitter to repeat the transmission. So this is automatic repeat request. So these methods, uh, it's not necessary that both should be used. Usually, one of these are used. The most common, of course, is the forward error correction, and automatic repeat request may be included along with forward error correction to increase the robustness or reliability of the system and the total communication system. Fine. Meaning, let's say I'm transmitting 15 bits. Let's say I'm transmitting 15 bits of data, and out of those 15 bits, if the particular code or the block code which I'm using has a capability to correct 3 errors, right? If the number of errors are more than 3, then the receiver will not be able to correct the error. But it might be able to detect that there were errors, and it can say that I have not been able to correct it. Then in that case it can ask for a repeat transmission. So the automatic repeat request in conjunction with a forward error correction can be helpful in improving the reliability of the system. But of course, as many schemes that you introduce, for error correction, the delay associated with the system will also increase. Or in other words, you need to increase the bandwidth, or the pulse widths need to be smaller. So this is the penalty that you get with complex systems which introduce forward error correction or automatic repeat request. So this is a block diagram of how the automatic repeat request works. There is a transmitter, there is a controller at the transmitter end and a controller at the receiver end, and there would be a feedback channel. So if the receiver detects that there is an error and have not been able to correct it, or if the decoder
చేయబడిన అల్లు అర్జున్ సినిమాలకు మంచి ఆదరణ లభించింది. ఇదే క్రమంలో ఈ సినిమా కూడా సూపర్ రెస్పాన్స్ దక్కుతుంది. నార్త్ ఇండియాలో పుష్పరాజ్ హవా నడుస్తుంది.
I'm getting some voice, someone using some news app also. Okay, so if the receiver, if the controller at the receiver detects that there is some well, I think you're tired of listening to my lecture now. Well, let's stop here for the day. And do you have any queries that we can discuss? Anything you would like to discuss? Anything you have not understood? हाँ? कितनी क्लास चल रहा है? 5 मिनट. So, do you have anything you would like to ask? I still see that there are 65 students who are present here. Out of 120, this is somehow not working out. No questions? Everything is clear? If there are no questions, then you all can leave today and get fresh for your next class.